a lot of information about parameter learning. So how can we leverage them? The challenge with leveraging context, though, is that they're really hard to excite and plan over due to the sparsity and non-smooth nature of context. So the question that our work is trying to answer is how can we plan and excite context modes in differentiable simulations for accurate and efficient parameter learning? So to summarize what we're doing, we propose an experimental design approach that optimizes context modes by maximizing a context-aware Fisher information, which directly reduces a lower bound on parameter uncertainty. So how do we do this? So we first like to address the underlying problem, which is the context-aware maximum likelihood problem, where we like to max the log likelihood function, where our likelihood function is a measurement likelihood model of some output of a sensor. So this captures a variance of our sensor, and we constrain this to physics. So our initial conditions, our sensor model, our dynamics model, and our context model, where X is states, controls are U, context force are lambda, and the parameters that we want to estimate is theta. So the goal here is to find a control sequence U that excites context, that maximizes the information about data. So we have to pass in data into this problem, and we want to get a really accurate estimate of data. So before we do this, we'd like to define what Fisher information is in the first place. So the Fisher information is a lower bound on the variance of the posterior of the maximum likelihood problem. So conceptually, it quantifies information richness in our data set D about parameter theta, so how much information is in our data, and we approximate this empirically as the outer product of the score functions, where the score function is the log likelihood model, gradient with respect to theta, and tau consists of our trajectory, our controls, and our resulting contact force. So the Fisher information provides a tight lower bound on the confidence ellipsoid. So if we have a confidence ellipsoid of just two parameters, then we reduce our variance, our confidence ellipsoid collapses. So if we maximize our Fisher information, we can reduce the variance of our parameter estimates, thus collapsing our confidence ellipsoid. So how do we optimize over this? So we'd like to optimize over the Fisher information or a matrix operation over the Fisher information because it can yield to more meaningful and diverse data sets, and it enables more effective learning. And we do this subject to physics, so our initial condition, and dynamics, and our contact model of choice. So our results regard experiments conducted and compared with a uniform random sampling based method as a baseline. And we implement a self-context model of the problem. So our problem statements here, we've introduced two different problems. One problem is a block throwing problem, where we like to throw a block with unknown mass, unknown shape, in the base context of a flat ground. And all we have access to in terms of our sensors are accelerometer. And so the question is, what is the right throw to make that excites the most information-rich context that can best describe our unknown parameters data? Similarly, we do this with a more of a control problem where we'd like to control our three-link planar arm with unknown mass and length of the links that happens to be contacting a nearby wall, and all we have access to is a contact sensor. So more meaningful context yields accurate parameter estimates. We define our accelerometer sensor model as just the transformation to our sensor Jacobian, given with Q double dot as consisting of our mass matrix and our biases. And we define this similarly with our contact force sensor model for our planar three-link arm. And we can see that given the same throw, for example, we're able to capture the same exact trajectory in contact behaviors given our parameter estimate priors that we get after running our algorithm compared to our random sampling baseline. And we see this similarly with our planar three-link arm experiments. So we evaluate this over 20 experimental runs. And we can see on the left two figures over our 20 experimental runs on the x-axis, we can see convergence, better convergence of our parameter estimates, which leads to higher information gain. And the overall intuition behind this is that we can see that if we excite these red terms in the score function, as well as in our contact model, we essentially use Q or our state as a free variable to maximize those gradients. And that leads to an emergent behavior that is information rich. So in summary, we present a guided approach to optimize for a context that maximize a contact or information metric We facilitate improved and enhanced parameter learning through emergent robot behavior that meaningfully interacts with the environment. And then we compare our experimental design approach with a random sampling baseline for a planar block throwing problem, as well as a non-prehensile manipulation problem. And here are my references. Thank you, and I'm open to more discussion.